Right, good afternoon and welcome back. As introduced this morning, I'm Chris Edsall and I'm presenting this short workshop on a topic that's very dear to Dominic's heart. So I'm very glad he let me do this one. I'm not sure I'm going to do it justice. So if Dominic at the end there's some things I've missed out that you would like to impart to the room, you can. Hopefully we'll have a little bit of time for Q&A. To be honest, I haven't run this material through before, so I'm not entirely sure it will fit. So we'll see how we go. But anyway, testing, super important, because we have an idea of what we think we've told the computer to do, but that's not how computers operate. We think, and then we type into a text editor, and that produces a program, and the computer runs the program. That's a reasonably lossy process. There are some things that, the computer's not a human, it doesn't think like we do. There are some things that we think were self-obvious to any rational being, but the computers aren't well, they're super rational beings. They do exactly what the code tells them, not necessarily exactly what you wanted them to do. And so testing is one way of helping to bridge that gap, to have some more assurance. You never, well, at least with testing you can't prove, but it will give you more sort of statistical confidence that the code is doing what you think it ought to do. So we've had I should have tested my presentation. There we go. Okay, so I'm going to use the mouse, not the keyboard. Good to know. So this is the goal. The idea is we want to make sure our research is of high quality and ensure that our software is of high quality to do that. Why in particular? There's been, over the past few years, a growing realization that a lot of research isn't replicable. If somebody comes along and tries to reproduce a result that some other researcher has done, they quite often fail. And some of these are to do with experiment design, conditions that are sort of to do with different domains, but some of it's computational. So there are some computational results that don't replicate either. What could happen if your software doesn't do what you think it says it does is you might assume it did, produce a paper or series of papers, have them published, and then find out after the fact that it was all based on wrongness, and have to retract them. So if you do some testing, what that can give you, and not just you, but also your collaborators, give you a reassurance that that your code is good. If you do have testing, it means that other people will respect your code a little bit more. So one thing I quite often do, if I need to use a library, I'll go onto GitHub, I'll look at various libraries which implement the function I want, and then I'll just throw in the bin any of them that don't have tests. That's their absolute minimum bar they've got across. Then there are some other things you look at, like do they have lots of an active community, does it have documentation, does it have license, etc. But if it doesn't have tests, I'm just not using it. So if you're producing code that you would hope other people would use, do absolutely test it. The other thing that you can gain an advantage in is in the software development life cycle. So you write some code and you run some tests and you make some releases, etc. The earlier in that process, if you order it in the conventional way from left to right with time increasing to the right, the earlier you catch a bug, the easier it is to fix, the less expensive by some metrics. In the industry, they've got this phrase called shift left. And the idea is you want to move all of that bug finding work further left in the software development lifecycle earlier, so that it's cheaper. So here's just some screenshots of people who have had to retract their paper. or papers because software has gone wrong. You don't want to be in that place. So that's why you should test, but what is testing? What sorts of testing are available? And so in this community, we come across the science test case quite frequently. So that's where you'll take your model and you'll run it. I'm thinking of climate models as my example here. You'll take a climate model, you'll set it up with a configuration, you'll run it forward for 20 simulated, well, you spin it up for 10 model years because you spin it up from 0, and then you run your experiment for 10 more model years, and then you look at the outputs, the fields files. You say, does this, have the quasi-biennial oscillation in the right place, or does this indicate El Nino or La Nina in the right years? And this is a valid test, but it's not really what we mean by software engineers as a test. It's too hard to tell from the terabytes of output you might get from a climate model whether something is right or wrong. And most people just eyeball it. So they'll put it into their plotting program, they'll put two plots, they'll put them side by side and say, yes, this looks right, or no, this doesn't look right. And I've actually got an example where that didn't work, where we had that method of testing and it tripped us up. So we were using the UK Met Office's unified model. It produces its own data format called PP files. And we made a converter to convert it to NetCDF, a more common data format. And then we plotted the results. So we looked at temperature and humidity and rainfall and pressure and all of those things, and they all looked good. And we ran this for 6 months in production until one day we wanted to look at level 0 or 1. I can't remember. It's Fortran, so it was probably 1. And it was off by 1 error. And so at all the other heights, everything was perfectly fine, but at the very bottommost height, the data were rubbish. But we didn't look at, we only ever plotted higher heights, and we never saw that. So eyeballing, it's a technique, but it's not the be-all and end-all of testing. And so we have some other techniques in software engineering. One thing you can do is an integration test. This does sound like the last thing, but in our case, take the climate model case, what we'd say is do the setup, then just run the climate model one time step forward, be it 5 minutes or 30 minutes or whatever your delta T is. Don't worry about the science results. You don't care what the temperatures and pressures are. Just run it forward and make sure that after one time step, the numbers that should have gone up have gone up, and the numbers that should have gone down have gone down. If you have a particular conserved quantity like energy, the total energy at the next time step is equal to the total energy at the time step before, and that tests all of the climate model, probably, depending on there might be some code paths that have if there are dependencies that you might not hit, going from time step 0 to time step 1. But it tests a significant fraction of the code, and it tests it together, so it makes sure that all the pieces of the code integrate. That's a good test to do. That should pass. If it doesn't pass, you've got a problem, because your climate model might be a million lines of code. Somewhere in the million lines of code there's a bug, but an integration test doesn't really pinpoint that. But you have one bit of information that the model's broken, which you didn't have before. So integration tests can be time consuming. The other end of the spectrum, and what we're going to look at mostly today, is unit tests. And the idea here is that you test the smallest fraction of your program that makes sense to divide it into. It's probably too small to test every assembly language instruction that your program compiles down to. It's probably too small to test every single line. But a common thing in languages with functions is to test every function. And ideally, you would not have functions that were 2,000, 10,000 lines long. Your functions should probably fit onto a screen or so of code, 10 to 30 lines. That's an ideal size to consider to be a unit. And one of the reasons this is better is the tests you can write are much simpler. You have to concentrate on far fewer things if you're just testing the set the pressure to 0 function. There's only one thing you really need to test that does it, sets the pressure to 0. You don't care about all of the other things that might be going on in your code. And it's much easier to reason about the test cases because everything's so small, because it's contained. This should run a lot quicker than an integration. A single unit test should run a lot quicker than an integration test. If you get good at this, you'll wind up with thousands of unit tests, and you may then have to group them. You may find that some of your unit tests run really quickly, and some of them run a little bit slowly, and you can split them into, say, 2 groups and run all the fast cases every time you do a commit. Maybe run the slower cases before you do a push. There's a thing in the industry called test-driven development, where they invert the process of writing the code and then writing the test. They write the test first before any code exists, and that should fail. If you've got no code and you've got a test that passes, then your test is wrong. So the idea of test-driven development, you write the failing test first, and then you write enough code to make the test pass. That has the wonderful benefit if you know when to stop. So sometimes you might get deep into coding, and it's 4 o'clock in the afternoon, and you start doing your thing, and then suddenly it's 2 in the morning, and you go, oh wow, I forgot to eat. And test-driven development will stop that, because every time you hit a point where all your tests agree, I can go get a coffee now, or I can go have dinner. You write just enough code to implement the functionality that you've decided that is required. To be honest, I've never seen test-driven development done in science. I don't know if anybody develops it.
I've seen it, but only if you can borrow somebody else's tests.
Only if you can...
When you borrow somebody else's tests.
Okay.
You can wax their test suite and then make sure that you still get the same results.
So for the recording, Valentine says he has seen it, but only when you can borrow someone else's tests. So he hasn't written the tests himself, hasn't done TDD himself first.
We'll have a little bit of a demo of the test-driven development style on Thursday with me and Ben in the ping pong mode.
So for the stream, Dominic is advertising his talk later on in the week, where there will be some test-driven development between him and Ben. An advantage of unit tests is, well, a catch with unit tests is that it's hard to come in after the fact, after somebody's written a monolithic program not designed with testing in mind, and then insert the unit tests. That's hard work. The benefit is, once you've done that, it sort of forces a modularity on the code. So if you write it so that if you adapt or refactor your code such that unit tests are, the functions are quite small and the unit tests, they're unit testable, then that has the side effect of making the architecture of the code slightly nicer, slightly more modular. What do you put in a unit test? Because it's a little bit obvious what you do in a science test case. You're domain experts, you do what you would do. But if you're testing a small fragment of code, what are sensible tests to write? The first one is, it would be good if you had a sort of known good example. And one of those is usually sufficient. If you know the answer that the function's supposed to get, you test it, gets that answer good. That gives you some confidence the function's working the right way, but not an awful lot, because we've all seen bugs where one example works and others don't. The places where the bugs are likely to hide in the extreme values of the things you feed into the function, or the extreme values of the things you expect out of the function. including nulls and null pointers and unusual things like that. So yeah, you test for max int, test for 0, test for the minimum integer, if it's integers, equivalent for floats. The other one, they're called edge cases, and for normal software developers, that's just a term, but for us, that really quite often does mean the edge. So if you've got a domain decomposition and you've got a box, you want to test on each of the edges, and you want to test the corner cases, which again for us are literal corner cases. You want to test where 0, 0 and your max x and max y, and if you've not got a 2D thing, if you've got an n-dimensional problem, you want to test the corners of all your n dimensions. Casper gave me a hint at lunchtime that quite often if you've got a stencil code where you're looking at your north and south and east and west neighbours, you test those. If you've got a star-based stencil code, remember to test the diagonal ones as well. Another sort of test is called a regression test. So a regression is a technical term to mean it's not working the way it used to. And some of the ways it might not work in correctness. So you didn't have a bug, you did some refactoring on your code, and now you do have a bug. And a really common case where that happens is when you're fixing a bug. So you're fixing one part of the code and you accidentally reintroduce a bug you've had before. So that's a particularly common case. Another way your code can regress is it just doesn't run as fast as it used to. Sometimes that's on purpose, you're adding more features in and the code does more, and so it takes longer to run. But sometimes it's accidental. You just iterate the wrong way over a matrix and hit the slow way around. So this is a piece of code that we have at Cambridge called Phoenix. It's finite element code, and they run a performance test on 5 sizes of jobs from 1 to 16 nodes, I think, on every commit. And so the numbers are too small for you to see, but basically the x-axis is time that's the figure of merit, you want that to be low, and the y-axis is date, and that's 2 years worth of check-ins to that repository. And you can see that they had a real win somewhere in 2021, where the performance greatly increased, so the time went down. And then somewhere in July 2022, something happened and the performance really dropped off. But the good news is they're checking that all the time and they're able to quickly fix, undo whatever it was that caused that performance regression. There's some other types of testing. There was a program written in the 80s, I think, to test operating systems. So in an operating system, the user land will call a function like open a file, and you call the open file system call, and you give it the file system number you want, the inode on the file system or whatever. And so they wrote this program called Crash Me, which just called random syscalls with random inputs. And the operating systems at the time were not robust to having that random input. So that's called fuzz testing. It's also used nowadays quite a lot in security. So if you have, say, an image library like a JPEG processor, you throw random stuff at that, and quite often, if it hasn't been written with this sort of defensive thing in mind, you'll be able to crash it with random input. Sometimes you might not have the access to the source code, so you can't write useful tests that way. The best you can do is a so-called golden output test. So you run the thing, you capture the output, and then at a later date, you can run the thing again, capture the new output, and diff them somehow. Sometimes that's as good as you can do, but that's a test. A really interesting one is called property-based testing. So I said before, try and think about the corner cases, you can actually get the computer to generate cases for you. So this came from a Haskell program called QuickCheck originally, and it's now in most languages. The Python implementation of property-based testing is called Hypothesis. And it'll give you some handy generating functions that would say generate an infinite number of integers or infinite number of floats or an infinite number of text strings, and then you can feed those into your function that you're testing and see if it survives. And that's quite helpful because when you're thinking about strings, you might think about uppercase or lowercase, or maybe if you're European, putting a few accents on some characters. But the Hypothesis library will put in all the Unicode non-printable characters and emoji and things like that. The other thing it does, so by default, the Python Hypothesis thing generates 100 test cases of sort of varying length. When it finds a failure, it'll go through those randomly generated test cases and reduce them. And so it'll give you the minimum failing case, which is it's super useful. We don't have time to do Hypothesis this afternoon. It would be really cool if we did, but maybe talk to me about it later, and we can arrange that for some later date. And this is a quote from a computer scientist, Ed just to show that, to point out that testing can't give you 100% assurance. It can only increase your confidence that you've got fewer bugs. It can't prove that you have no bugs. Even so, it's better to do testing than to not do testing. Somewhat of a hard sell to stand up here and tell you that you ought to write more code because you've already written your science code, and I'm saying you should write even more code for no obvious science benefits. The benefit is you don't have to retract your papers. But how much effort should you put into the testing? How much do you test? Should you test every single line of code, every path through your code? I think Dominic and I had a minor disagreement here. I think I don't think even Dominic is saying that you should test 100%. I think there's a diminishing return the more you do test. And I think we settled on a figure of 95% coverage would be 90 to 95%, says Dominic. Valentin.
It's actually worse because you might not, it's a combinatorial explosion. You might have 100% test coverage, but you're only covering 10% of the possible combinations of inputs. So instead of chasing 100%, think about what are the critical parts that you care about.
So for the recording, Valentin says that even with 100% line coverage, the combinatorial explosion of possible configurations that your program could run in means you're not getting all of them. So in the case of Python, the library that you want to use is called coverage, and if your command line before said PyTest something or other, we'll get onto that in a minute, you'd adapt it to say Python minus n coverage. It's in the README. So you basically just put the coverage command in front of your PyTest command, and it'll track which of the lines are covered. This isn't just a Python thing, obviously. Pretty much every language with a test suite has a coverage library, so you can get those figures out. You'll quite often see it on GitHub repos, on the badges that they put at the top of their README. Quite often you'll see the percentage coverage from a coverage tool. You could write tests using a language function like assert by hand, and that works. And in some situations, that may be all you've got, and so you should do that if that's all you've got. But we quite often have better, more ergonomic frameworks. They can do things like when an assertion fails, show you what the failing input was and what the expected output was. They can collect together large numbers of failing cases and sort of summarize that and tell you, you had 1,000 failed cases or whatever, rather than listing each of the 1,000. They'll allow you to group tests, to run subsets of tests. Like I said, you could run just the fast ones, or run the slow ones, or run ones which require a supercomputer, or ones which will only fit on a laptop. And yeah, they have handy functions like assert almost equal, because you don't want to be comparing two floating point numbers for exact equality, or the difference between two floating point numbers to 0. You want to ensure that some epsilon threshold, and so it gives you handy utility functions like that. And it'll also help you with things that aren't related to the test, but are related to the infrastructure of the tests. So-called fixtures. A common one in non-science domains is setting up and tearing down a database, which is an expensive operation, so you don't want to do that 1,000 times, and you don't want 1,000 setups and teardowns of a database and populations of the database in a loop. You just want to do that once, run your 1,000 tests, and then throw the database away. And so a fixture will help you do that. In our case, a more common one is downloading a large file. So you don't want to download terabytes for every test in your test suite. Getting on to the frameworks we have, Python has one built in. It's called unit test. No one uses it. Sorry, to a close approximation. The third-party library PyTest is much more convenient. It's got less boilerplate. So if you were to write the same test, the number of lines of code you'd need if you were doing it in PyTest is much smaller than unit tests. That's the one I advise you use. There are a lot of testing frameworks for C++. Some popular ones are Google Test and Catch2. We're going to do an exercise this afternoon with Catch2 because version 2 of Catch2 has a nice property that it can be implemented as a single header file, and so the installation is download one file, which if you've dealt with C++ libraries before, that's on one end of the spectrum of how complex they can be. For Fortran, I don't actually have a recommendation currently because I haven't done much Fortran testing. If you go to the Fortran language people have sort of rejuvenated the Fortran language. They've got a website, fortranlang.org. They've now got a package manager. And if you have a look at what's in the package manager, there are some unit testing frameworks. There's one called Veggies, because they think that testing is like eating your veggies. And because there's one called Veggies, there's also one called Garden. There's one called Fruit. There's one called Toast, and I've got no idea what that relates to. Anyway, there are a few around. If you have that use case, try them out. Let me know, because I'd be interested to know. I have no recommendation for Fortran, and specifically because Valentin was in the audience, I said that Julia has a built-in one in the standard library called Test. Do you advocate the Julia standard library built-in one?
Yeah, that's the most commonly used, and if you just open the package manager and then type in test, it will automatically run that. There are some experiments for more parallel testing, but this is the tried and true one that everybody's using for CI.
So summary for the recording, yes. The standard library test one package in Julia is the one that's the Julia developers.
So for the Fortran one, my only recommendation is pick up the one which doesn't have
You can do it for the recording.
So Fortran one, my only recommendation is pick one which doesn't have too much dependency, because for example we don't want to have Fortran which unit testing depends on the Python. And you spend time setting up your Python framework. So a few frameworks which just depend on the C and Fortran compilers.
Sure. So actually, I got over the motivational bit before. Hopefully, I've convinced you that it's worth attempting to test your code. And so, for those who are game, we're going to try. So we're going to see if we've got PyTest. Can I have Actually, can I have a show of hands? Who's using a Windows laptop? Hooray! Oh.
Far positives. I have seen few Windows here.
Because the instructions I've got are definitely tested on Ubuntu and will probably work on a Mac, but the Windows ones are mostly similar, but you've got to put the slashes the other way around. You've got to say .ps1 instead of when you source the thing. So you might already have PyTest available. So can you give it a go? Can you type PyTest -v and see what happens? And if you succeed, if you get output from PyTest with a version number, I was going to say raise your hand, but we've got a fist of celebration for that. We've got 2. Okay, so for everybody who tried but didn't get it, then you're going to need to install it. I've given 2 choices here. I prefer the top one, even though it's slightly more lines of code. The virtual environment method. If Conda is more to your choice, we've got a Conda method as well. So pick one of those, whichever floats your boat. I've got here CD Python because I've assumed you've already downloaded the Git repo, which we're going to have the tests in. So actually, Dominic's shaking his head. Can you?
Well, maybe we need to tell everyone what that is.
Yes. Where do we find it?
It's linked from the resources section of the web page.
Testing. No, that's. Sorry, I'm going to do this while looking behind myself. So if you go to the ICCS GitHub, there should be a new one called testing. It's not a popular repo yet.
That's the top.
There we go. So if you git clone this URL, it's possibly a bit small for you to read, but it's off the Cambridge ICCS thing. It's called testing. That will give you a directory called Python, which we can CD into. So I'll give people 60 seconds or so to find that and clone it. This was a software carpentry course. I'd get you to put green sticky notes up if you'd succeeded and red ones if you hadn't. But maybe what we'll do is raise your hand if you've got difficulty. I'll assume that the Git training from this morning worked and everybody can Git clone a repo. So if we go back to the there we go. So after you've cloned it, cd into the Python directory, run python -m VM to load the VM module, and then you give it a name. When I'm not doing training exercises, I prefer to put my Python virtual environments in my home directory. This will put it in the current directory. What that does is it makes a new directory structure, copies the Python binary in, and some small number of libraries that it needs to bootstrap the rest of it. You type source, the name of your environment. I've called it PyTest env, and underneath that there's a bin directory, and inside that there's a shell. It's not a script; it's a fragment of shell called activate, and so you source that. If you do that, your command prompt should change. So you should get whatever was your command prompt prepended with round brackets and the name of the Python virtual environment, PyTest env. And then you want to install into that the packages that we need. There's only 2, PyTest and requests, using pip, so pip install -r requirements.txt. So again, I'll give you a minute or so to attempt that. Stick your hand up if you would like some help.
is it also fine just to do a sort of native pip install and not go into a virtual environment, Python VM?
It is, if you want to mess up your laptop like that, go I prefer to put things in a virtual environment because I switch between projects so often and they all have different and conflicting sets of packages. So,
You checked in access into the Python directory.
Did I?
It's existing one there called access.
Oh dear.
Unless I missed that.
Ignore the, yeah. I didn't intend to do that. Thank you for pointing that out, Simon. That's an anti-pattern you probably shouldn't check in your virtual environments. This is why I normally put them on my home directory.
So, git ignore.
Yes.
Teaching moment. And on the slide, the spelling for requirements in the second example as well.
Thank you. So you raise a good point. Git ignore, which we didn't have this morning. And that's a special file you can use to tell Git to not suggest that you add a file and to not automatically add a file when you're doing git add. And depending on your language, there are different sort of conventions for hidden files and in Python's case, messy files like cache files. And you can actually go on to, you can type git ignore space your language into GitHub and find a template file, and that's exactly what I did, because I can't remember all that off the top of my head. So you ignore _py caches and py.class and all of this. And of course, because I'm not accustomed to having my environments in the same directory as my source code, that's why I accidentally checked it. So yes, you can actually remove that py test end environment, because what's on my laptop's unlikely to be exactly the same as what's on yours. So if we go back to the slides, so we need to spell requirements the conventional way. If you type pip install -r rec hit tab, it should auto complete the correct name for you. And yes, rm -rf, the pytest end that you got when you cloned the repo, because that's mine and it's bad. Sorry. Maybe if we could have a show of hands for people who are ready. Okay, and for people who still need a bit of time, that's enough that we can probably move on. For those that did need to install, which is almost everyone, now you should be able to run PyTest and get some output. Cool. So in the source code there's a file called mycode.py. I've been a bit lazy and I've just put all the tests in together with the code. If you had a larger test suite, you'd probably separate those out. So you'd have the implementation and then you'd have the tests. PyTest will do a recursive directory search from below where you are, and it'll look for file names of the form something or other _test or .py or test _ something or other .py. I prefer so the second case reads more like English. So if you've got some foo code to test, you'd have a test _foo Python file. But then when you list them in directory order, in name order, it sorts all the tests together separate from the implementation. So I actually prefer to write it as implementation _test. So then the implementation and the test are side by side in the directory. But anyway, we don't have enough tests or files for that to be a problem here. So did everybody successfully run PyTest now? Getting a lot of nodding and some double thumbs up, so we'll move on. Let's add a test. So if you have a look at the mycode.py file, you'll see that there's one test already there. I think we're testing that 6 divided by 2 is equal to 3 or something, and therefore the divide function works. So let's add a new test. You can see in the source code there's a comment that says exercise 2. What you want to do is define a new function called test underscore something or other. And in that function, assert that dividing any integer you like, your favorite integer, could be 42, could be not, dividing any integer by 1 gives that same integer back again. It's somebody's back restarting. That's probably not the expected result of the test.
Hard crash.
I was sort of assuming everybody in the room had had contact with Python and understands Python at the level they can sort of copy paste a function to another one, change some things. It's the hardcore C++ people got an exercise later on.
No, they've got issue. They've got
I was waiting until people stopped typing, but Jacob's typing something else. I don't think he's doing his testing. So, who has successfully divided an integer by 1 and got the integer back again? Okay, I'll give people a few more minutes.
yeah. We just know it's not running in like this. Just thing 0 collected.
Can you run?
Are you getting?
I changed the test.
Oh, you viewed it on
We're supposed to write our own test. I'm not clear on this.
So you get a test?
No, I got a zero. But I think the test was supposed to be
So I need to. So if I apply test and the name of the file of the sorry, I missed a step out there. In the test directory, there's this mycode.py and also the answers. I changed to put those up so if I run a test. Okay. Just going to mirror these slides to make it easy for me to debug.
say PyTest descends through the directory. It looks for test underscore.
Yeah. You can also give it PyTest space the name of the file, which is what I was doing. But yes, it will automatically find tests files that start
They
testing.
have to start with test.
Yeah.
Or we put
Okay, that's fine. Okay.
but then this is too simple. Test file, which is the same.
So we should do PyTest micro.py.
Yeah. And because I was testing the answers, not testing with the exercises, no, you can't see that.
I was just going to do range. So how are you going to make the test on the template?
So if you don't want to run a test, you can use the this magic decorator. On top of it, you can write PyTest mark skip in front of them. And that's in fact what I want to do for exercise 4, because we haven't got to that yet, so we don't want to run either of those tests. And then if I run Python, right, it's PyTest mycode.py. What it prints out here is a green full stop for the passing test case, and a yellow S, the ones that are skipped. That's if all your tests are either passing or skipped, that's usually enough information. If you've got failing test cases, that's not enough. It'll print the failing ones, but you can, if you give it the -v flag, it'll be more verbose and it'll tell you what the names of tests were that passed and were skipped. So, has anybody been able to get some output that looks something like that? Got one thumbs up at the back of the room in front of you. A few thumbs up. Okay.
We're doing something a bit more complicated here.
I'll leave you to it. Yes, the chap with the hand up in the green. Yeah.
I might have misunderstood things. I was trying to create a test for an engineering integer.
That's.
You'll actually get a losing error.
Yeah.
So I just have like n by 1.
So that's very good. What you've accidentally done there is reinvented property-based testing. So you've obviously got the property-based testing mindset, which is good because after you've been doing example-based unit testing, which this thing is where you feed it, one input and expect one good output, getting your head around trying to do all the integers is a bit mind-bending. So it's good that you're thinking that way. So that's the bit in green. If we were to try and write a test that satisfied it for all integers, that would be a property saying that the property of division is that there's for integers is there's an identity for division. So if I were to do this, I might say, exercise 2. I did it already. I checked in the answer. So the test is to make sure that if you take 6 and divide it by 1, you get 6. You might have chosen instead of 6, you might have chosen 42 or any other integer. But that is a test. Let's go to the next page. So sometimes the data that you're feeding your function isn't good data, but you want your function to be able to deal with that, to recognize what bad data is and do the right thing. So some languages like C++ and Python have exceptions. So your code can say this isn't a normal run-of-the-mill thing. This is an exception to the normal processing, and they have a range of exceptions that they can throw. And what you can do is check that the function that you've got correctly recognizes the exceptional input. The problem we've got in Python is this would normally crash if it's an uncaught exception, it would normally kill the interpreter and dump you back at the shell. So what we can do is PyTest can check this inside of a context. So that's a Python thing where you say with this thing. Normally, the way you normally see it is with files. So with some file operation equals F, and it gives you back a file handle which will automatically clean up because the context handle does it. In the case of PyTest, the context handler will catch these exceptions which would normally stop the interpreter and check that the correct exception has been raised. So you use this function pytest.raises, and you give it the name of your exception you're expecting the function to call, and then you call the function and hope that it does actually do that. So exercise number 3 is to test that divide function again and make sure that when the denominator, I think dividing by is 0, it does actually raise, in Python it's called a zero division error with that capitalization. And so what you need to do is uncomment that line that says pytest_mark.skip to make sure it does actually run the test, and then insert your test code where it says insert your test code here, and it should look vaguely like that.
So I'm not a fan of this one. I mean, it's okay. I mean, it just non-returns taggers lead you down that road where you think everything's fine, and then you know, and it sort of makes it difficult to introduce things. Like imagine if the CI said, "Oh, this is labels," and you do it locally in passes, like not having it. I mean, they could be random as long as it's just deterministic.
Yeah, it's like to see.
Yeah, I mean, we could just do it and take the bank, but yeah, we could fix the seed.
If you're fixing the seed, then you know you get that.
Yeah.
But if you're fixing the seed, then you don't need to random.
But that's kind of
So I've lost the centre of the room who've gone off on a discussion about determinism or non-determinism in testing, which probably indicates they've completed exercise 3. Can I have a show of hands who has completed exercise 3? Yay. Who needs more time? No one. Right. That I guess means we go on to exercise 4 will be after what I explain a fixture is. I mentioned it earlier. It sets up a resource that can be reused between multiple tests. The common one is setting up a database. Here we're going to download a large file. It's not a particularly large file, it's only 76 kilobytes, but let's pretend it's 76 terabytes, and that you would only want to do it once. To do that, you write a function to do whatever setup you want, and you decorate it with the @pytest.fixture command. And then when you want to use that fixture in the test, you have def test underscore whatever your test name is, and in the round brackets you put the name of the fixture, whatever you called it. And so the exercise I haven't written here, but we go to the source code. In exercise 4, what we want to do is download this file here with all the possible words that can be used in the game of Wordle, and make a fixture called Wordle underscore words. It doesn't have to be called that, but that's what I suggest you call it, because it does have to match down here. So this is the name of the fixture. So before that line, we want a function that's def Wordle underscore words, but decorated with the fixture thing, and returns the list of words. So the top here, we need to import requests. So we're going to download something in Python.
You're missing an I.
Thanks, I can't actually see the corner of the screen from this. Import requests, and then get URL. And I don't know how complex I want to make this. I think given the amount of time we've got left, well, we've got half an hour, so I can make you suffer, but I will give you because Casper and I suffered, you don't have to. The thing you want there is, so you use the request library to get a requests object. The actual result of downloading it is in this attribute rec.text. And if you want to convert that, so that's just one big long string. If you want to convert that into lines, you want to say rec.text.splitlines. Yes. So about approximately where I put that, define a function, decorate it, and see if you can get these tests to pass. In the list that I downloaded, the first word in inverted commas is AAHED, and the last one is Cynic.
The fixture should return the.
Indeed.
So that function, the name of that function is an argument.
Yes. It's a bit weird.
No. No, interesting. No. Skip some tests. Okay, now. Who tests the test?
definitely the ones you just.
So can I get the usual show of hands for those that are playing along and who has succeeded? Yay. Who needs more time? 0 people. So, hang on, do this way around. See, so the answer was to take out these so that so you can see how horrible I am at them. At PyTest dot fixture, I'll call it word_words. I'll type it the same as and we're going to basically say rec requests dot get that big long thing. And then we're going to say return. I should have another window open with the answers because I did this an hour ago and I might not get it right the first time. Rec dot text dot split lines. And this all has gone well. Yes, the first word was AEN, whatever it was, and the last word was Zymic. So there are more fixtures available. So to see what the built-in ones are, you can run PyTest -- fixtures. And it's got all sorts of things about temporary paths and caching files and things like that. So we downloaded our pretend enormous file once, but we could download once per run of the whole test suite, but we could actually cache it between test suite runs and other things like that. So have a look at the documentation for more on those. Okay, now we're really going to test the audience. C++. So the library I'm suggesting we use for testing C++ code is called Catch2. As I said, at the moment, you can install it just by downloading the single file, the HPB file. It's boost licensed, so if the code that you're putting it into is compatible with the boost library, that's good. You should check that. Otherwise, you might need to choose a different test suite. In the, if you go up 2 directories from where you are, if you're in Python tests, if you go up 2 directories, there's a directory called C++ in the repository, and it has a make file, and if you run make fetch, it should download the .hpp file. If you run make, it should run the, it should build a program called test case, and then if you run it, you should see some tests passing or failing.
It doesn't actually matter if you checked in catch.hpp.
It doesn't. I tried not to. You should maybe, yeah.
It puts it somewhere else.
Yeah.
Test case binary is checked in as well. So make will fail. So if you do make dash B, capital B, it will override and rebuild it for your platform.
Thank you. I will demo that for people who see it first. So if we go up 2 directories, down to C++ directory. I've checked in a whole bunch of stuff. If I type,
I know, I put my students like the first week.
am I worse than your first week students?
No, we're just extolling the virtues of add-p over here.
So I should not have checked in the binary. That's a rookie mistake. My make file, I think, has a make clean target. And so then you can make, or equivalently, as Dominic said, you could make -b to override it. And so if we run test case, we see we have some cases that pass and some that fail. At least one that fails. So there's mouse test case CPV line 12 failed. It requires that factorial of 0 equals 1, and 0 is not equal to 1. And so the exercise here is to look at the test case.cpp file and see if you can change the definition of the factorial function such that it does now pass the test cases. So the base case of factorial of 0 is 1 is a special case. And since I stole this from the Catch2 tutorial webpage, it's got the answer already in, so look at the commented code. Probably in this room, I don't need to say. In some other audiences, I would, because they're familiar with interpreted languages only, and so editing the source code and then rerunning the tests will do what's required here. Because it's C++ and it's compiled, you edit the source code, you have to rebuild the tests binary. I get a show of hands who has their C++ factorial function now passing all tests? A smattering of hands. I'll give it a minute or so. Fortunately, we've got 15 minutes left in the session, so we can have an extended Q&A. This is also fortunately the last exercise.
I do know this. Are you going to show us coverage?
No, because I haven't set it up, and it's almost certainly, given everything else that's gone on this afternoon, it's almost certainly going to fail. But if you have a pre-canned coverage test you would set up you'd like to demo,
Okay.
let me get into. So if we have a look at the repository for Catch2, at the top of their README, there's this thing here that says code cov. It has 92% code coverage, which they consider to be green. Now if we go through this as a third-party website, which will show you what your coverage looks like from your test cases, since this is the tests of Catch2 itself. And for each file, deep down. So the lines covered green are covered by test cases, and the ones that aren't presumably are not.
Yeah.
Let's run on my.
Yes.
They don't show their coverage. Does anyone know a Python library which has coverage stats?
We're just making a version that we can use with coverage.
Right. Who now has a version of factorial that passes all tests? Fewer hands than before, so we have a regression. I think that means it's coming up towards 5 o'clock, and that's enough C++ for people this afternoon. So just some hints I found when talking to people about testing. If you run pytest --PDB, it will drop you into the Python debugger PDB when a test fails. So you can get straight into debugging. Some advice from Casper: if you find a bug and you fix it, put in a test case which exercises that bug. And this is when I was talking before about regression, quite often re-triggering a bug you had previously. So if you fix a bug, definitely put in a test case for it. You can configure your, so we've been running tests on the command line, which is a bit hardcore. If you want something a bit more ergonomic, you can configure most IDEs now to run tests. So VS Code understands PyTest and Catch2 and Google Test. You should probably run the tests as often as you can put up with. The slower they are, the more that'll put into your run, compile, debug cycle. But you should probably test before you commit. So it'd be ideal if you didn't commit failing programs. And certainly before you push. So if you're collaborating with people, it's a real faux pas to break the build to push things that don't compile or have incorrect running characteristics. You can configure Git to automatically do something when you commit. It's a so-called commit hook. A common case for this is to use a formatter. So if you and your collaborators disagree about tabs versus spaces or how many spaces there should be, you can actually get to rewrite the source files on the way in and the way out of the repository, so everybody's happy. Yes, I said run test before pushing. That's the material I have for this afternoon. We've got 10 minutes before the short talks. Dominic, should we do Q&A or?
Yeah.
Yeah. I have a microphone. Who would like to discuss testing? Orally.
How far do we have to go? Because we can see with the examples that we can test. We have in mind, and the coverage stuff is like you have a test associated to your code, but is it enough to test really? So I think it seems to me that the coverage is a bit not maybe artificial. Like, okay, there is a test. Is it the best test for this code? So two questions.
So I think that sort of came up earlier when we said that even with 100% coverage, you're not testing everything. And also with the property-based testing, you can have a little bit more assurance that you're covering more cases than with the example-based testing. But I go back to the quote from earlier that testing can't prove the absence of bugs. The more testing you do, the more confidence you have. I guess, if you were writing avionics software for Boeing, you'd probably prefer to do more testing. If you were writing a one-off script to manage some text, you might not want to do any testing. So it's context dependent. But if you would like to add or disagree.
Well, I suppose one thing to slightly enrich that is that coverage checking is about control flow. It's which lines are being executed in your program, but it doesn't tell you about the coverage in terms of the data, which I sort of what I'm saying there as well. So this divide example that Chris has been doing, the divide 0 case, if we remove that, the coverage checker would still say 100%. But that 0 one is really important for the data within the domain. So coverage checking is a good, I believe it's a good thing, but it's not the be all and end all because of the data space as well. There's control flow rather than the data flow thing.
Also, as soon as you start thinking about sharing your code, I think that's definitely when you should put tests in. Because, okay, the tests are telling you that you know that the code is doing what. More importantly, if you share it, then it tells the person who shared it that it's doing what you say it's doing. So that's definitely, I think, a hard line.
Yeah, 2 points I wanted to make is you can make testing arbitrarily complex. So you can start with fuzzing, and then you can do SMT solver-based fuzzing to make sure that you truly get every possible test case. That's not normally necessary, but if you're writing code for Boeing, maybe think about that. We all appreciate that. The second point is documentation can also include code, and you can generate figures and examples from your documentation, and you want to make sure that if you have something like that, you actually include that in your test suite so that when your users read your documentation, they actually have working code in there instead of the thing that used to work 3 versions ago. That is a really powerful way of also generating more test cases because you're explaining how you think somebody should use your library. You have maybe a science test case in there, and it enables your users to actually use your library. We found that very powerful.
it depends on the language. There are different frameworks for making that. Yeah, you have to find the right thing for your language, but we've done that. It's been really useful as well to avoid your docs getting stuck.
I was trying to unlock my laptop to show you that, but I apparently have locked myself out. Python, it's been that kind of afternoon. Python has one called doc tests. It used to be standalone and is now a plugin to PyTest. And yes, as you said, it's a really powerful tool for making sure your documentation is current. So the thing about PyTest, doc test, if you write your documentation in restructured text, it understands that, and it understands the Python interactive interpreter prompt, the 3 chevrons, and the ... dots when you have an incomplete structure. And so you can basically construct your test case by going into the REPL, the interpreter, doing your thing, cutting and pasting it straight into your documentation, and then always running PyTest ensures that documentation is up to date.
So it's like dual purpose, right? Because you're making sure your docs don't get stale, but it also encourages putting examples in your code so people know how what the functions do. It's good documentation. I think we'll do a coverage thing. I think Ben and I have something that uses the PyTest coverage as well. Well, we can have it in.
Cool. We've got
Cool. Let's have a brief reader before the short talks then. Which will start at 5 o'clock. So 5-minute quick break.